name is Viva. I'm talking to you about a new technology from GC Green Carbon called our Total Stack solution. And what I've done here is just very quickly assembled some paper shapes, because generally if you can make it out of paper it can be engineered or designed. And I've kept it as simple as I can, but I will just start working from your left over to your right. Here is the stack. This would be a conventional stack, could be natural gas, particularly coal we're interested in because of the high CO2 content. And so what we have in our total stack solution is an induction fan which will draw the flue off, and when it's not in play there would be trapdoors in the stack so that it could still vent while this is all offline. And then at the induction fan it goes down into a two-story building. This is the top story, and inside here are cooling fins through which the flue gas goes into and is very quickly cooled by some dry ice pelletizing machines, which are these large units here that would be delivering dry ice down onto the cooling fins. So they're there. Then once the ice is sublimated off of the heat from the smokestack, it's brought over into what's called a cooling tunnel recovery tunnel. And then what happens is you repressurize the gas once you have compressors over at the back end of the tunnel, pulling the sublimated dry ice back into liquefied form, or actually on this whole system the CO2 only needs to go to 90 pounds or 100 pounds per square inch compression or pressure to work anywhere in this system. So essentially once you get it compressed you can put it into a tank field over here of CO2, which is going to now become a working fluid. Okay, so this is some CO2 that's being stored and is utilized again for the dry ice cooling, and it is looped this way here. The flue gas has of course gone through the cooling fins that are in the first part, what happens is the flue gas is then taken to a scrubbing tower where hydroxide oxide tanks here at the back of this here have been generating what's called hydroxide ions in water to scrub the flue gas in the cooling tower. Once the scrubbing is completed, then it takes off any particulate or a little bit of sulfur, that kind of thing, and will capture it as a fluid which will be cleaned up and looped back here for the hydroxide ions in water. So the water is actually looped around to the factory where we make the oxide ions that are delivered into water, and they form hydroxide ions very quickly in water, and that is the scrubbing system. In between there, before it gets wet, we have a carbon filter which is replenishable either with natural carbon, or we can have some of these units on site making carbon and have a continuous in-house supply of carbon filtering before it goes up to the scrubbing tower. Once the flue gas is scrubbed, then we have what are called alumina drying systems, and they can either be silica or alumina, and they're usually a long tubular tank which will fill up with water, because alumina and silica are hygroscopic. They like to collect water, so you have a bank of these beds and you alternate from full to empty, and you just need to warm them up to vent off the water. So everybody understands that. And this talk is actually designed for people who have some technical background or have worked on a large facility and know the whole overall technological things, such as an alumina bed for drying and stripping water. Once the water is stripped, then there is a two-stage separation process There's a membrane, it's called the metal membrane from Air Liquide and Praxair, and they have what's called a fast gas separation system. So essentially what we do is we take what is now water, CO2 and NO2, and we run it through these membranes, not once but twice. So you have a substantial installation of these, so you get that trade-off curve maximized on those technologies. There is a little bit of a trade-off, so that's why you want to do it twice. Then we take the CO2 over this way, the water's been stripped, and we take the NO2 over to these reducers over here. These vessels here are now Green Carbon's patented technology, and it's called a carbon and oxygen separator and a nitrogen and oxygen separator. We have found that these separators can with almost perfect efficiency separate CO2 back into carbon and oxygen. So what this does, even though there is a speed limit on this technology, is we can run out many of these vessels and tie them together because they're not expensive to make and they do not require a lot of energy because they have 4 catalysts in them. So the catalysts can be easily economized, and these things can be running, and so you can scale this out very quickly, and you can add on as you go. So you can start small and grow larger. Okay, essentially what you want to do with the size is, if you have a 100 megawatt original power plant with coal, you want to fill this all up with 100 tons of carbon, which is 3.36 times of that is the weight of CO2, so 300 tons of CO2 circulating in this system, and you'll see how that's going to fit. Okay, so we can separate the carbon and the oxygen over here, and then we're going to make use of the carbon and the oxygen as an oxycarbon fuel. So what we're going to do is we're going to turn the oxycarbon fuel, which is carbon plasma and oxygen plasma, bring it back together and burn it in this here facility, which is your typical furnace with a boiler with a working fluid of what I recommend, which is CO2 for this site, because then we're working with a consistent working fluid throughout the whole site. And so essentially what we do is with a working fluid as CO2 for the turbine, we go to a Brayton turbine. So the next facility will be a combination between holding the Brayton turbines and generating power, and at the bottom cooling the warmed up CO2 that was warmed up by the oxycarbon fuel here. Over here it is warmed up because we've made some dry ice to cool it off, and we need to keep cycling. So what we're going to do is we're going to continue with the CO2 now. We want to take the burnt CO2 exhaust and cool it off. So we have a facility here at the back with dry ice pelletizers. And in this facility we have dry ice inside of tanks, which is being warmed up. That's a proprietary system where we get non-compressor enhanced pressurized carbon dioxide. Then we can bring them out and we can actually do a staged recompression over here back into the CO2 tank. Okay, so that's how the CO2 is used. And then from here the CO2 can actually, once the full facility is fully loaded and fully secured with CO2 as the working fluid, then the stack here can be rested. and turned off. So we have scoped out that the original coal-fired power plant only needs to be running 10 to 15% of what it was before, so that it will keep this topped up and keep the fuel going. Now, what makes it so efficient is the carbon and oxygen separator, which is got catalysts that make it about 98% efficient, allow a continuous recycling of the CO2 as carbon and oxygen as a plasma fuel, and then back to CO2 again, stored up, and then turned and looped around and around and around right here. And the only thing that requires energy at that point is the separator, which is highly efficient. So then you have, essentially you can take 100 megawatts and 367 tons of CO2 into a system like this with a very large tank field, and you can have CO2 as a renewable fuel. And there's going to be a little bit of slippage when tanks or equipment is moved about or disconnects. It's mostly a turnkey system, so you're going to be able to hold that gas within the containment, use it as a fuel, separate it, create the feedstock right on site, and thereby lowering the requirement of the original stack by 85% comfortably, and going on to a very simple system here where, because of the catalysts in the separators here, these vessels being 98% efficient and the plasma system being highly efficient with the Brayton cycle and CO2 as a working fluid, it can be probably done 10 times around and even more, and will not have a negative energy cost. And it's not a perpetual energy machine, because you have to install energy to heat up these vessels to get them going. But once they're going, they're highly efficient. And when you turn them off, you also lose heat. So when they go offline for servicing, there's an inefficiency there. And we take advantage of the entropy that the fire creates with the oxycarbon fuel, which we reverse the entropy here and make the oxygen and carbon from CO2. So thankfully the catalysts have been so successful in lowering the energy cost that this is actually commercially viable. So also the nitrogen and oxygen separators, which are a part of our proprietary technology as well, they have the main job of providing oxygen for the oxide plant, which is inside this trailer type facility, where we would simply pipe the oxide gas over to here and then do our hydroxide making process here and do the scrubbing. So the nitrous oxide, the NOx, will be a source of oxygen and will provide nitrogen gas as well if there's any requirement for that. It can be given commercially, or it can be released back into the atmosphere as the main natural atmospheric constituent we live with. So this is basically the Cliff Notes version of a 3D model that I would love to do at some point, but computer models cost $30,000 to $40,000. We have done some scoping on what is required in terms of how many vessels here, and we have proven that the oxycarbon plasma does burn, and we're doing more work on that. So essentially the technical risk here is very interesting. It's either off the shelf or the technical risk has been removed. So this is what we have so far. So what we can do if we have government policy now where we're going to take coal plants offline because they cannot be clean, what I'm recommending we do is we keep them online for 10 to 15% of the time, take their CO2 out of the flue gas. Many of them have already done mercury, already done sulfur. So we can come in, pull the rest of it through this system, get it over here and separate it into carbon and oxygen, burn it as a very highly efficient fuel with only CO2 as the exhaust, keep that exhaust captured, recompress it through a special dry icing technique, and then provide it back to the separator so that the fuel can go around. And at 98% efficiency, you can get a lot of energy gain out of this new technique. So what we've done here is, don't worry about CO2, let's use it. This is the philosophy behind this suite of components and technology. And I will probably be doing a part 2 to this once my engineers see this film. We're going to discuss some of the engineering Q&As that come out of that, and I will post that as well for the people who are invited to view this video. And I thank you very much for your time, and have a nice day. Bye-bye.